Good morning, one and all, honors physics students, to another video by Mr. Finn, Honors Physics. This will be for Monday, March 23rd, 2020. Hope you guys are doing well out there. Hope you had a great weekend. A couple of announcements first. Number one, we do not need to send the written bookwork through email. Actually, I just want your questions. If there's something that you don't quite get on what you're doing, send me those questions. I can address those in other videos upcoming this week. But we're going to hang on to our written homework at this time, and we'll try to do one big collection when we all get together again. On that subject, we need to also take a worst case scenario here, process, and assume that we will not be back to school for the remainder of the school year. Now, if that's the case, we need to actually have some kind of mechanism for gaining the physics credit, because it's a possibility that the Michigan Department of Education will come down and say, you haven't been in school this time, either we're going to prolong school into the summer, or these kids are going to have to take this semester over again. Well, if that's the case, I'd like you guys to be able to all test out of honors physics by testing on the material that we're doing now. So we need to make sure that we're up on our schoolwork, and you're completing these videos and lessons so that we can test out if need be. Okay? All right. For today, question of the day: how does sound travel in different mediums? Let's have a little think about that. Hopefully that you guys saw the video that we had posted with regards to the movie Stand By Me, where the guys are going through the railroad track, and then the kid finds out that there's a train coming. And how does he find out that there's a train coming? He doesn't hear the train. He's listening for the train in the track. Okay? Then there's a subsequent video on speed of sound in different medium, which I'm going to cover in this lesson now. So, let's take a little look-see at our magic board. Okay, guys, let's talk a little bit about sound in different medium. Now, if you viewed that video, you saw that a young man was putting his hand on the rail, and he was putting his ear on the rail. Now, why would that be? Well, that's because sound travels at different speeds in different mediums according to a relationship based on the elasticity of the material and the density of the material. So what if the material is the same, like air? Well, the denser the air, then the less sound will travel. And so when is air less dense? Well, when the temperature is higher, the molecules are running faster, and of course, less dense as you become a higher temperature. So therefore, air with a higher temperature actually transmits sound better than air of a lesser temperature. But what if we're changing materials? If we're changing materials, we're going from air into water or air into steel. Well, this is an air. In the air, you are hearing the sound of this vibration through the air as it gets to you. Now we know from previous examples that speed is about 343 meters per second, which is actually 331 meters per second plus 0.6 meters per second for every degree Celsius above zero. So that's our speed of sound in air. But what if it was traveling through a different medium like water or steel? Well, there's a relationship. The bulk modulus represents the elasticity of the material, and the density is represented by the symbol rho. So we might have to have a density difference based on temperature, but you can get an average density difference for most materials in your book. Which is more important though, bulk modulus or density? Let's have a little think about that. Okay guys, let's talk a little bit about our winner here. Turns out the bulk modulus is the big winner. The elasticity of the material is almost always more important than the density of the material. Let's take out some materials for ourselves. Well, if the velocity of sound is dependent on bulk modulus and density, if the bulk modulus is bigger, that means you have a bigger numerator than you have a denominator. So B is much, much bigger due to the fact that the molecules are closely packed and those vibrations get sent at a much greater rate. Then the density wouldn't make as much difference. So a bigger numerator, even if the denominator is increasing, means that this overall product is going to increase. Let's check out some numbers here. If we just take our basic x equals vx times t, or distance equals speed times time, in air, 343 meters per second times a 4-second difference would yield about 1,400 meters. So if the train was 4 seconds away in the air, those young lads on the train track would get about 1,400 meters of notice. Now, if the train is traveling 50 or 60 miles an hour, that might not give you a whole lot of notice. However, if it were water, like a submarine, or you could hear a tick in the water, some kind of tap or something, or even a sonar device, the velocity of water, speed of sound of water, is roughly about 1,520 meters per second. So 1,520 meters per second times the same 4 seconds gives you roughly 6,100 meters of notice. You may recall some of those old World War II movies where there's subs and there's destroyers above, and they're sending little pings down to determine whether the sub is there, and everyone has to shut everything off of the sub and they have to be quiet because the speed of sound of water can actually be detected just underneath the surface of the water much easier than it could through air. For this very reason. Lastly, let's check out the steel values. Steel, according to the values in your book, about 4,500 meters per second. That's pretty big. If you multiply by that 4-second difference, that same 4-second difference, 4,500 meters per second times 4 seconds gives you roughly 18,000 meters that wave would travel in 4 seconds of time. So you can see that the young lad feeling for the vibration in the steel track for the train versus hearing it with his ear in the track versus hearing it in the air, a much bigger value. Of course, in Hollywood, they really didn't show you that because he really put his hand on the steel track and then about 2 seconds later, he saw the train, which is kind of ridiculous. But it's a good movie clip and you guys should view that on the Google Doc if you get a chance. I hope this helps. Bulk modulus, way more important than rho density, and that should give you guys a little bit of help with some of those questions on the homework problems. If you have issues with those, please send them in, and we'll talk about speed of sound in closed tubes and open tubes tomorrow. Okay, thanks for tuning in, guys.